Right. So few things. What is that we were doing last class? The last two classes that we were doing is what is known as the integration. So initially we started with what is known as a simple function. Well, this is a measure space. So this is a simple function. And once you know that this is a simple function, then there is a natural way to write this. Right? This is the canonical representation, and therefore the integral of this is defined as summation 1 to n alpha I mu ei. Right. So this is how it is defined. And then the second stage we looked at to 0 comma infinity. This is just a Borel measurable function. So in that case we defined integral over omega f d mu as supremum over integral over omega g d lambda g d mu, such that 0 less than or equal to g less than or equal to f, and g is a simple measurable function. Right. So this is how we define. So few things that we observed. First thing is that if f is simple, then the two definitions coincide. Right. And then, so we were trying to do some properties. First thing is that if you have two measurable functions, positive Borel measure, extended real valued positive Borel measurable functions, f and g, with f less than or equal to g, implies integral over omega f d mu is less than or equal to integral over omega g d mu. Yes. How does this follow?
Since f is less than equals to g, every set, every element in the set integral over.
Yes.
I mean for f, every element in the set for f will be in g as well.
Yes. So if you have a function phi which is less than or equal to f, then it is also less than or equal to g, and that tells us that this inequality is valid. Right. Right. Second one is that if c greater than or equal to 0, then integral over omega c times f d mu is equal to c times integral over omega f d mu. Yes. So one thing that you'll have to notice is that if g is less than or equal to f, then c times g is less than or equal to c times f. Similarly, if g is less than or equal to c times f, then, well, if c is non-zero, if c is 0, then there is nothing. So let's assume that c is non-zero, then 1 by c times g is less than or equal to f. And only thing is that 1 by c times g is also simple. So these observations will tell you that you have this equality. The last one is f plus g d mu is equal to integral over omega f d mu plus integral over omega g d mu. Right. Yeah. So how do you show this? No, you cannot do this now. No, you cannot do this now. This part requires something else. Yeah, so maybe we'll prove this one. Huh? Those two can be proved easily. Yeah, so these two, if you have understood, fine, or else I'm just leaving it as an exercise. Right. Now, the next one is one of the important theorems in the context of integration. In fact, one of the pillar stones or cornerstones, whatever you can say. Monotone convergence theorem. Right. So let Fn be a sequence of 0 to infinity valued Borel measurable functions defined on omega a mu. That means that there is a measure space omega a mu and these functions are defined on omega such that Fn is less than or equal to Fn plus 1 for all n in, then integral over omega omega limit of Fn d mu is less than, well, in fact, y less than or equal to limit of integral over omega Fn d mu. Yes. Yeah. Right. So now let's get into the proof. So this is one of the theorems which says that the limit and the integral, they can be interchanged. So this is one of the very powerful theorems. Since Fn is an increasing sequence, it is clear that Fn is less than or equal to limit m tending to infinity Fm for all n in n. Yes. So this is true for all n. So whatever be the limit, this is, so that implies. So, and I have a function which is bigger than Fn for all n. So that implies that integral over omega by the monotonicity Fn d mu is less than or equal to integral over omega limit m tending to infinity Fn. And this is true for all n. And this is true for all n. And therefore this implies. So let me integral over omega Fn d mu. So this is again less than or equal to integral over omega Fn. Right. So we are done with one inequality. Right. So we now establish the other way inequality. Right. Let's do that. So we now establish the reverse inequality. Right. So let alpha belong to 0, 1, and also let g be a simple function such that 0 less than or equal to g less than or equal to. So all these fn's, they all are measurable, therefore the limit is also measurable. This is just the point-wise limit, and therefore this is measurable. Right. For m and n, let En equal to, although x and omega, so that fnx is bigger than or equal to alpha times gx. First thing, here are some simple observations. So what can you say about the sets En's? En and En plus 1. Fn's are increasing, therefore
En is a decreasing sequence.
decreasing sequence.
I mean,
Increasing
Increasing or decreasing?
increasing.
Yes, Dev Ranjan.
Yes.
Huh?
Yes, sir, it will be increasing.
Increasing. Why is it increasing?
So because for n plus 1, fn plus 1x will be greater than fnx.
Exactly.
And so
Yeah, Fn's are, they are increasing sequence, right? That's what the statement says. The Fn's are increasing, and that tells us that these En's are increasing. So the sets En's are increasing. Second, what will happen to the union?
whole omega.
Whole of omega. Why? Whole of omega. Why? Because Fn's they increase
Alpha
to
of gx is
G is
sir,
something
alpha.
which is less than or equal to the limit, and Fn's they increase to the limit. So that tells us that this is going to be whole of omega, right? So I'll simply say verify. Right. Therefore, having observed these two, so integral over omega Fn, this is bigger than or equal to integral over omega Fn chi En. And well, this is same as integral over En Fn. So I am dropping this d mu because it is clear that we are integrating with respect to the measure mu. Right. Now this is integration of Fn over the set En, and on En, Fn's are bigger than or equal to alpha times gx. Therefore, this is bigger than or equal to integral over En alpha times gx alpha times g, and g is a simple function, and therefore this alpha comes out. This is true for all. And fine. Now, first thing to be observed is that we have already shown that this one. So since E going to integral over E g d mu, what is that we know? This is a
Measure.
This is a measure, right? This is a measure. And the ENs are increasing. These are increasing. We have, so this is true, so therefore limit n tending to infinity integral over En g d mu, Ens they are increasing, and therefore this is same as integral over omega g d mu. So which immediately tells us that this is true for all n in n. Therefore, if I take the limit integral over omega Fn, this is bigger than or equal to alpha times integral over omega g. Right. So this is true for every simple function g. So well, so this is true for every simple function g such that 0 less than or equal to g less than or equal to limit right. Now taking supremum over all such simple functions, if you take supremum over all such simple functions, then you can notice that limit n tending to infinity, well, I should have added one more line, but it doesn't matter. Right, so limit Fn. So now this is true for every alpha between 0 and 1. So letting alpha tend to 1, we get the reverse inequality. This is true for every alpha, therefore let your alpha tend to 1, and that's it, that's what we wanted, right? Now let's prove what we wanted, where we left. In fact, so this is the place, maybe I'll put it as a first corollary. Yeah. Let f from, in fact, even in the last class we were discussing this, that it was tempting for us to define it as limit of integral over omega fn d mu, where fn is a sequence of simple measurable functions which are increasing and they increase to f. Yes, so in fact, so that is not wrong. That's what we are going to see. Infinity be a measurable function if fn is a sequence of simple measurable functions such that 0 less than or equal to fn and they increase to f, then integral over omega f coincides with limit n tending to infinity integral over omega fn d. So this is a simple consequence of what is known as the so-called monotone convergence theorem. Alright, so again, as a corollary to this, what do we have? So let f comma g from omega to 0 comma infinity be two measurable functions, then integral over omega f plus g same as integral over omega f plus integral over omega g. Yes, so how do you show this? How do you prove this? How do you show this? If fn converges to f and gn converges to g, fn plus gn will converge to
F plus g.
f plus g, and therefore
Like f and gn exist, and there some will be measurable and measurable, so this will be this inequality holds.
right. So if, and also if fn and gr are simple, then if f and g are simple, then what will happen to f plus g? F plus g is also simple, right? So use that, use the previous corollary to finish the proof of this, right? Next one.
Sir, sir, if we have two sequences fn and gn which converges to f and g respectively, I mean increases to f and g respectively, but then if we take integral over omega fn plus gn,
Mm-hmm.
how can we distribute integral over the sum?
So that we
Which
have
is
done, sir, in starting of our class.
which sum are you talking about? I don't know.
Sir, integral over fn plus gn, we have to take the limit. I mean,
These are
but
simple.
oh, fn and gn are simple. Okay, okay.
Because we know that there exists a simple sequence of simple functions which converges TF. And similarly, you know that there exists a sequence of simple functions Gn which converges to G.
Yes,
right?
sir. Okay, okay.
That's what we are
Got it.
using. If Fn is an infinite sequence, of measurable functions, defined on omega, then integral over omega summation Fn is same as summation integral over omega. Well, all these are positive. That is very important. Yeah, positive. That is very important. Yes. Yes. So how do you prove this?
So we can take sum as a limit of finite sum, limit and tends to infinity
Exactly.
and finite sum.
So use
Using
Gn as
above
the,
parameter.
let Gn be the partial sum I equal to 1 to n Fn Fi, and all because Fn's are positive, Gn's are positive, and Gn's they increase to summation over nn and Fn, and then use monotone convergence theorem and the previous corollary to finish the proof, right? Yeah. Right. Fine. So this is what we have been discussing. So if f from AB to R plus is continuous and bounded, then integral A to B f, in fact fx dx equal to 0 implies f equal to 0. This is known to us. This is one of the standard theorems of Riemann integration that we did, or standard result of Riemann integration. All right. Now let's look at this one. He in fact saw an example of a function which is bounded but not continuous. This is again part of the theory of Riemann integration. 1 if x is 0, 0 if x non-zero. Now it is immediate. So that integral over omega f. So you integrate with respect to the Lebesgue measure. This is 0. Why is it 0? Why is it 0? Why is it 0?
Because measure of singleton 0 is 0. I mean, I can write as in canonical form and then.
So this is same as integral over omega f into characteristic function of I'll say open 0, 1 close to 1 plus characteristic function of singleton 0. Dm. Now using linearity, one can again split it as integral over omega f into characteristic function of 0, 1 dm plus integral over omega f into characteristic function at singleton 0. So now this is same as integral open 0 close to 1 f dm plus integral over singleton 0 f dm. Right? Now on this whole of 0 to 1, open 0 close to 1, the function is 0. So this is 0 plus, and then the measure of singleton 0 is just 0. So this is going to be 1 times measure of singleton 0. So this is going to be just 0. Right. So although we have a non-zero function, the integral is 0. But something more can be said. It is not 0, but something more can be said. What can you say about this function?
It is 0 almost everywhere.
Exactly. It is 0 almost everywhere. Right. So, and that's exactly the conclusion of our next one. Yes. So this proposition will tell you the same thing. Let f from omega to 0, infinity be measurable. Then integral over omega f d mu is 0 if and only if f equal to 0, mu almost everywhere. Yes, so this is one of the important theorems. Right, so case 1, suppose that f is a simple function. So let me write f as summation 1 to n alpha I chi ei. So this is the canonical representation with all the alpha i's being greater than or equal to 0. Right. This is the canonical representation of f. Now, given integral over omega f d mu equal to 0. Well, sorry, this is equal to 0. So this is equivalent to saying that summation 1 to n alpha I chi ei, mu of ei, this is 0, right? And all alpha i's, mu ei's, they all are positive. That tells us that alpha I mu ei, this is also again greater than or equal to 0. So this is, I have a sum of positive numbers and this sum is equal to 0, and therefore each and every term should be equal to 0. So this is equivalent to 0. It's equivalent to saying that for each 1 less than or equal to I less than or equal to n, either alpha I is 0 or mu of ei is 0. If alpha I is 0, then the value of the function at that point is 0. If alpha I is non-zero, then mu of ei is 0. which means that wherever f is non-zero, the measure of that set is going to be 0, which is equivalent to saying that f is identically 0 mu almost everywhere. Right. Now let's look at case 2. So let f from omega to 0 comma infinity be an arbitrary measurable function. Right. Well, now let's prove the forward part. Suppose that integral over omega f d mu is 0. Right. So note that set of all x in omega such that fx is non-zero is same as saying that because all these are 0 to infinity greater than 0 is same as union over n in n, all those x in omega such that fx is bigger than 1 by n. Therefore, if measure of this set, measure of x in omega such that fx is bigger than 1 by n, sorry, bigger than 0, is greater than 0. So once you know that this set is bigger than 0, has got measure positive, then there exists n naught. You get at least one n naught in n such that measure of omega such that fx bigger than 1 by n naught. This is bigger than 0. Further, so once you have this, f is strictly bigger than 1 by n naught times chi, characteristic function of all those x in omega, such that fx is bigger than 1 by n naught. Right. So let me call this as en naught. Then f is bigger than 1 by n naught times chi en. Right. Therefore, integral over omega f d mu is bigger than integral over omega 1 by n naught times chi en naught d mu, which is same as 1 by n naught times measure of en naught. 1 by n naught is greater than 0 and measure of en naught is again greater than 0. Therefore, this whole thing is greater than 0, which is a contradiction. Correct. Now let's prove the.
So,
Huh?
how f is strictly greater than 1 by n naught chi of, I mean, it would be greater than equal to?
No, because on E naught we have chosen it as 1 by fx is bigger than 1 by n naught.
Okay.
Right?
Yes, sir.
Now let's prove the backward part. Suppose that f equal to 0 mu almost everywhere. So let phi from omega to infinity be a simple function, in fact be any simple function such that 0 less than or equal to phi less than or equal to f. Now, since f equal to 0, mu almost everywhere, this immediately implies that phi is 0, mu almost everywhere, which implies that integral over omega phi d mu is 0 by part 1, by case 1. Right, so which immediately tells us that because phi is an arbitrary simple function, this is true for all phi with the property that 0 less than or equal to phi less than or equal to f, therefore integral over omega f d mu is 0. That's it, done. And we are done. Yeah, so with this, let me stop this lecture.